So this is the second part of the Mycobacteria lecture, and we're going to continue discussing our pigmentation and the photoreactivity of these organisms. So Mycobacterium tuberculosis, one of our major pathogens among the mycobacteria, is non-chromogenic and non-photoreactive. It does not produce a pigment at all, even if it's exposed to a light source. So that is very important to know. You need to know that Mycobacterium tuberculosis is a non-chromogen. It's called buff colored. Now, there are organisms that are reactive either when they're exposed to the light or not exposed to the light. So, Mycobacterium scrofulation is a scotochromogen. It's going to produce pigment when it's exposed to the light. It's going to produce a pigment even if it's in complete darkness. And Mycobacterium consacii is photoreactive. It's going to produce a pigment in the light. If you keep it in darkness, it's not going to produce a pigment. However, if you then expose it to light, the pigment will start to come out. So that's photoreactivity or a photochromogen. Now, a lot of the non-chromogens are slow-growing mycobacterium organisms. We already mentioned the Mycobacterium tuberculosis is a non-chromogen, but so is Mycobacterium avium, Mycobacterium bovis, Mycobacterium ulcerans, the organisms in the Mycobacterium terrae complex, Mycobacterium gastri, Mycobacterium malminans, and there are some rapid growers that are also non-chromogens, and that is the Mycobacterium coloni and Mycobacterium fortuitum. Scotochromogens, those organisms that produce pigment only, whether it's in light and dark, it always produces pigment. The slow growers are Mycobacterium gordoni, Zolgai, Scrofulation, and Xenopi, and the rapid growers are Flea and Smegmatis. And the photochromogens only produce pigment if they're exposed to light are Consacii, Marinum, Simii, and Asiaticum. Now, there are several biochemical tests that can be done for the Mycobacteria organisms. There's the niacin, the nitrate reduction, the catalase, and there's several different catalase methods that can be done. Tween 80 hydrolysis, Tellurite reduction, Arylsulfatase, and probes. So the niacin tests for the production of niacin. You have it. This is a liquid-based test. So you have your liquid from your culture. Add it to your niacin reagent, and if it turns yellow, it's positive. So your non-chromogenic and slow-growing organism that's niacin positive is always going to indicate a possible Mycobacterium tuberculosis. And usually in the clinical lab, that's what you're looking for. You're trying to rule out if an individual has Mycobacterium tuberculosis. So whenever you see a non-pigmented, slow-growing organism and it's niacin positive, that's an indication that you have Mycobacterium tuberculosis. So you should put a circle around that bullet point because that is something you definitely need to know for the next exam and also for your final exam. And the board exams always like to ask a question about Mycobacterium tuberculosis and the chromogenic, slow growing, and the fact that it's niacin positive. So here's a niacin test. Clear is negative and yellow is positive. Nitrate Reduction test detects the nitrate reductase enzyme, which reduces nitrate to nitrite, and a positive test is red. So the organisms that are nitrate reductase positive are Mycobacterium tuberculosis, Consacii, fortuitum, and Zolgai. So here's a typical nitrate reduction test where you have a clear is negative, slightly pink is considered 1 plus, a little bit of enzyme produced, 3 plus, and a 5 plus is bright pink. The catalase test. Now, to test for catalase, mycobacteria are catalase positive, but there are different ways to do a proper catalase test with Mycobacterium. So you can do the drop method where you take your hydrogen peroxide and drop it on colonies. However, your isoniazid resistant, isoniazid is one of the drugs used to treat tuberculosis. Strains that are isoniazid resistant tend to be negative using the drop method. You can do a semi-quantitative catalase test where you add Tween 80 to your hydrogen peroxide. You add it right to your Lowenstein-Jensen tube culture, and then you measure the height of the bubbles. There's also a heat stable catalase test where you add your hydrogen peroxide after you heat the organisms. That's not commonly done. So some of these catalase tests are not really done in a clinical laboratory, but it's still good to know about them. Your textbook still covers them. You can read about them in more detail in the textbook. So here is the semi-quantitative catalase test where you can put your hydrogen peroxide right directly into your growth, and then you can measure the height of the bubbles. So if you had your bubbles at a greater than 45 millimeter height, it would be indicative of being catalase positive for this test. Tween 80 hydrolysis tests for the production of the enzyme lipase through hydrolysis of the compound Tween 80. And this organism distinguishes your photochromogens, scotochromogens, and nonchromogens. So the pathogenic strains are usually Tween 80 hydrolysis negative. So whereas other strains are commonly Tween 80 hydrolysis positive. Tellurite reduction tests the ability of an organism to reduce tellurite, and this test is performed over a 3-day period. So it's not commonly done in the clinical lab anymore. Organisms in the Mycobacterium avium complex, which include Mycobacterium avium and intracellulare, and all of your rapid growers. So with your Mycobacterium, we have slow growers and we have rapid growers. The slow growing Mycobacterium take 4 to 6 weeks to grow on agar plates. The rapid growers can be visualized on agar plates within 2 to 5 days. So for tellurite reduction, all Mycobacterium avium complex and the rapid growers are positive. Urease, just like we've talked about for the gram-negative rods, urease testing can also be done where you get that bright pink test color in a positive urease. You can, on the right is that Tellurite reduction test that is no longer done in a clinical laboratory. There's the Arylsulfatase Test, which tests the ability of Mycobacterium to split phenolphthalein, which is another 3-day test, and it identifies Mycobacterium fortuitum and colonii. There's also a paraxinamidase test. There's an iron uptake test. So there's a lot of different tests that you can use for Mycobacterium, but because most clinical labs have those systems like BACTEC, SeptiCheck, Midget, they don't need to use all of these different biochemical tests anymore. Susceptibility testing is very important because if you do identify a pathogenic mycobacterium, you want to know if it's resistant to the antimycobacterial drugs. So this is a test that's going to be routinely performed. Usually your TB systems, your instruments are going to be able to do this test. You can do it manually by adding your antibiotics to your media and then seeing what or what organisms can grow and in what concentrations. So you compare your number of resistant organisms to your number of organisms that grow on plates that don't have any antibiotics. You can look at your organisms directly by making a smear and look at your acid fast staining, and your indirect methods to look at Mycobacterium is subculturing. But for susceptibility testing, usually it's going to be done in the systems. So this is a nice chart because it shows you the major organisms, if there's a pigment, the temperature range that they grow in, their rate of growth. So if it's weeks, it's a slow grower. If it's days, it's a rapid grower, as well as the colony type. So there are rough colonies and smooth colonies. And then niacin production test, and we already said Mycobacterium tuberculosis is positive. So we're going to move on to the third part.